700 million years after the Big Bang, the universe was still in its infancy. The first generations of stars had only recently begun filling the darkness with light. Galaxies were small, chemically primitive, and still assembling from clouds of hydrogen and helium. Yet inside one tiny object, astronomers have found a black hole with the mass of roughly 50 million suns. The object is called Abell 2744 QSO1. It is only about 1,300 light-years across. That makes it hundreds of times smaller than the Milky Way. But the black hole at its center contains at least two-thirds of the entire system's measured mass. There is very little evidence of a mature galaxy surrounding it. The gas is almost entirely hydrogen and helium. Heavy elements produced by generations of stars are nearly absent. The visible stellar population is far too small to explain how such an enormous black hole could already exist. This is not simply a large black hole inside a small galaxy. It may be a black hole that became enormous before most of its galaxy had even formed. For decades, astronomers believed that the first supermassive black holes probably began as the remains of massive stars. Those smaller black holes would then consume gas, collide with one another, and slowly grow inside developing galaxies. But QSO1 does not fit comfortably into that sequence. Its central black hole appears too massive, too early, and too dominant over its surroundings. It raises a question that once sounded almost backward. Did the first galaxies create their black holes? Or did some of the first black holes help create the galaxies around them? The answer is still uncertain. But the James Webb Space Telescope has now provided the strongest direct evidence that, in at least some early systems, the black hole may have come first. Webb launched aboard an Ariane 5 rocket on December 25, 2021. The telescope had taken decades to design, build, test, and prepare. Its 6.5-meter primary mirror was too large to fit inside any available rocket in its fully opened form. So engineers constructed it from 18 hexagonal segments that could fold together for launch. Its enormous 5-layer sunshield also had to be folded into a compact package. After Webb separated from its rocket, the observatory began one of the most complicated deployment sequences ever attempted in space. The solar array opened first, the communications antenna deployed, the supporting tower extended, the sunshield covers released. 2 large booms pulled the shield outward. Its 5 thin layers were then carefully separated and tensioned. Finally, the 2 folded wings of the primary mirror moved into position. There was no repair crew waiting nearby. Webb was traveling toward a region called the Second Sun-Earth Lagrange Point, or L2, approximately 1.5 million kilometers from Earth. Unlike Hubble, which orbits only a few hundred kilometers above our planet, Webb would be far beyond the reach of any currently planned crewed servicing mission. The deployment had to work, and it did. Webb does not sit motionless at L2. It travels in a large halo orbit around that region while moving around the Sun with Earth. This arrangement keeps the Sun, Earth, and Moon on the same side of the observatory. Webb can therefore position its sunshield between those warm objects and its sensitive mirrors and instruments. That protection is essential because Webb primarily observes infrared light. Infrared radiation carries information that human eyes cannot see. It can reveal cool objects, penetrate clouds of dust, and detect the highly stretched light of galaxies in the early universe. But warm telescopes also produce infrared radiation. If Webb's mirrors and instruments were too warm, their own heat would overwhelm the extremely faint signals arriving from deep space. Its sunshield prevents that from happening. Each of the 5 layers reflects and releases heat. The cold side of the observatory remains below approximately 50 Kelvin, or minus 223 degrees Celsius. Webb's near-infrared instruments operate at around 39 Kelvin. The mid-infrared instrument, known as MIRI, must become even colder. A closed-cycle helium cryocooler lowers it to approximately 7 Kelvin, or minus 266 degrees Celsius. This does not mean that Webb can operate forever without fuel. The telescope still uses propellant to maintain its orbit and manage its orientation. However, the Ariane 5 launch placed Webb on such an accurate path that relatively little fuel was needed for course corrections. Mission engineers estimate that the observatory may have enough propellant to support more than 20 years of science operations, although hardware health and the space environment could eventually create other limits. Webb carries several instruments, but two are especially important to the story of QS-01. The Near-Infrared Camera, or NIR-CAM, records detailed infrared images. It identifies faint galaxies and measures how their brightness changes across different wavelengths. The Near-Infrared Spectrograph, or NIR-SPEC, separates incoming light into a spectrum. A spectrum is far more than a colorful line. Every chemical element interacts with light in a distinctive way. By studying spectral features, astronomers can determine which elements are present, how hot the material is, how quickly it is moving, and whether gas is falling toward or flowing away from a black hole. NIR-SPEC also contains an integral field unit. Instead of measuring only one combined spectrum for an entire object, the integral field unit can collect spectral information from different positions across a small region of the sky. That ability allowed scientists to map the motion of gas inside QS-01. But before Webb could measure that gas, astronomers first had to find the object. QS-01 lies behind a massive collection of galaxies called Abell 2744, also known as Pandora's cluster. The cluster contains so much mass that it bends the space around it. Light traveling from a more distant object must pass through this curved region before reaching Earth. The light can be magnified, stretched, distorted, or divided into multiple images. This effect is called gravitational lensing. It acts like a natural cosmic telescope. Because of the precise alignment between QS-01, Pandora's cluster, and Earth, the distant object appears in three different locations in Webb's images. They are not three separate objects. They are three magnified views of the same source, created because its light followed different paths around the foreground cluster. Without this natural magnification, QS-01 would have been much more difficult to study. Its light began traveling toward us more than 13 billion years ago. We see the system as it existed only about 700 million years after the Big Bang. Initial NIR-SPEC observations confirmed that QS-01 contained an actively feeding black hole. Gas falling toward a black hole does not usually disappear quietly. Before crossing the event horizon, the material can form a rapidly moving accretion flow. Friction, compression, magnetic fields, and extreme gravitational forces heat the gas until it releases enormous amounts of radiation. That radiation can make a growing black hole visible across billions of light years. In 2024, researchers estimated that QS-01's black hole had a mass of approximately 40 million suns. That first estimate came from the width and behavior of emission lines in its spectrum. Gas moving close to a massive black hole can reach extraordinary speeds. The broader the spectral lines appear, the faster the gas may be moving. Astronomers combine that velocity information with estimates of the size and brightness of the emitting region to calculate the probable black hole mass. The method is useful, but it is indirect. It relies on relationships calibrated using black holes in the relatively nearby universe. Scientists could not be certain that those same relationships worked perfectly in an object seen during the universe's first billion years. Webb later gave them another method. Using NIR-SPEC's integral field unit, researchers mapped how hydrogen gas moved at different distances from the center of QS-01. One side of the gas was moving slightly toward us. The other side was moving away. More importantly, its orbital speed changed with distance in the pattern expected when most of the mass is concentrated in one central object. This is called Keplerian motion. The same basic relationship describes how planets orbit the Sun. Objects closer to the central mass move faster, while more distant objects move more slowly. By measuring this motion, scientists could calculate the central mass using gravity itself. The result was approximately 50 million times the mass of the Sun. This was the first direct dynamical measurement of a black hole mass from within the universe's first billion years. It also confirmed that the earlier indirect estimate had been reasonably accurate. But the mass was only part of the surprise. The black hole represents at least two-thirds of QSO-1's total measured mass. In nearby galaxies, the central supermassive black hole normally accounts for only a tiny fraction of the total galactic mass. The Milky Way, for example, contains hundreds of billions of stars and an enormous amount of gas, dust, and dark matter. Its central black hole, Sagittarius A star, has a mass of approximately 4 million suns. It is important to the region immediately surrounding it, but it does not contain most of the galaxy's mass. QSO-1 reverses that familiar relationship. Its black hole is not a small central component inside an enormous stellar system. The black hole dominates almost everything Webb can measure. The chemical composition made the picture even stranger. Stars manufacture heavier elements. The early universe began mainly with hydrogen and helium, along with tiny amounts of a few other light elements. Carbon, oxygen, silicon, iron, and many of the materials found in planets and living organisms were created later inside stars or during stellar explosions. A galaxy containing many generations of stars should therefore contain noticeable quantities of these heavier elements. QSO-1 does not. Its measured metallicity is less than half of 1% of the Sun's metallicity. In astronomical language, metallicity refers broadly to elements heavier than hydrogen and helium. The extremely low value suggests that QSO-1 had experienced very little previous star formation. There had not been enough time or enough stars to enrich the gas with large quantities of heavier elements. This creates a serious problem for the conventional light seed model of black hole growth. A light seed begins when a massive star reaches the end of its life and its core collapses. Depending on the star and the surrounding conditions, the result may be a black hole with a mass ranging from several suns to perhaps hundreds, or, in rare scenarios, around 1,000 suns. That seed can grow by consuming gas and merging with other black holes. But growth takes time. As material falls toward a black hole, the hot accretion flow releases radiation. That radiation pushes outward against the incoming gas. The approximate point at which outward radiation pressure balances inward gravitational attraction is known as the Eddington limit. The Eddington limit is not an absolutely unbreakable speed limit. Under certain conditions, black holes may temporarily grow at super-Eddington rates. Dense gas flows can trap radiation, and complicated accretion structures may allow material to enter faster than simple models predict. Even so, growing from a small stellar remnant to tens of millions of solar masses in only a few 100 million years is difficult. The seed would need to form extremely early, maintain a large and steady fuel supply, avoid being thrown out of its environment, and spend much of its existence growing near or above the conventional Eddington rate. QSO-1's lack of an established stellar population makes that story even harder. Where did the stars required to create the first seed go? Where are the remains of repeated stellar generations? Where are the heavy elements those stars should have produced? One possible answer is that the black hole did not begin as a normal stellar remnant. It may have started as a heavy seed. Under the right early universe conditions, an enormous cloud of primordial gas could collapse directly toward its center. Normally, cooling gas fragments into smaller clumps that eventually form many individual stars. But if cooling and fragmentation were suppressed, a much larger quantity of gas might collapse together. The result could be a massive object or black hole seed containing thousands, tens of thousands, or even hundreds of thousands of solar masses. Beginning with a heavy seed would dramatically reduce the amount of later growth required to reach 50 million solar masses. This is called the direct collapse scenario. Astronomers have discussed direct collapse black holes for years, but finding clear observational evidence has been extremely difficult. The required conditions may have been rare, The gas had to remain warm enough to resist fragmentation. Nearby radiation sources may have needed to destroy molecules that would otherwise cool the cloud. The environment also required a large supply of pristine gas with little contamination from earlier stars. QSO-1's extremely low metallicity and black hole-dominated mass make it an important candidate for this kind of origin. There is also a more speculative possibility. Some researchers have suggested that black holes may have formed from density fluctuations in the universe's first moments, without requiring stars or collapsing gas clouds. These hypothetical objects are called primordial black holes. Depending on the conditions, they could have formed across a wide range of masses. However, primordial black holes have not been confirmed as the explanation for QSO-1. Many versions of the idea are strongly constrained by other observations, and scientists still need much more evidence before connecting any particular early supermassive black hole to the first second after the Big Bang. The responsible conclusion is therefore not that Webb has proven exactly how QSO-1 formed. It has not. The important result is that ordinary gradual growth from small stellar remnants appears difficult to reconcile with the object's mass, age, chemistry, and limited host galaxy. QSO-1 seems to have been born large, or to have reached a large mass through a growth process far more efficient than the standard picture assumed. It may also be showing us a galaxy in reverse. Instead of a mature galaxy feeding and growing its central black hole, the black hole may be influencing the construction of the galaxy around it. A feeding black hole can release enormous amounts of energy. Radiation and outflows can heat nearby gas and push it away, limiting future star formation. Under different circumstances, those same forces can compress surrounding gas and help trigger the formation of new stars. Black holes and galaxies may therefore develop together through a complicated feedback process. QSO-1 could represent an extremely early phase of that relationship, before the surrounding galaxy had time to build a large stellar population. If it were the only object of its kind, astronomers might consider it an unusual exception. But Webb has found an entire population of mysterious compact sources known as little red dots. They began appearing in Webb data shortly after science operations started in 2022. In images, they often look like exactly what their name describes: tiny, reddish points of light. But their simple appearance hides a complicated identity. They are compact, they are bright, they are extremely distant, and many existed during the universe's first 1.5 billion years. Large samples suggest that little red dots became common around 600 million years after the Big Bang. Their numbers then declined rapidly by approximately 1.5 billion years after the beginning of the universe. That limited period may represent a previously unknown stage in the evolution of early galaxies and black holes. The red appearance can have several causes. Cosmic expansion stretches light from distant objects toward longer, redder wavelengths. Dust can also absorb shorter wavelengths and make an object appear red. In addition, dense gas surrounding an active black hole can absorb, scatter, and reprocess the energy coming from the accretion flow. At first, some little red dots seem to contain impossible quantities of stars. If all their light came from stellar populations, their galaxies would have assembled enormous masses faster than many models allowed. This led to headlines claiming that Webb had broken cosmology. But that conclusion was premature. A rapidly feeding black hole can produce tremendous brightness from a very small region. If astronomers mistakenly attribute that light to stars, they will overestimate the stellar mass of the galaxy. Once likely black hole-dominated sources are treated correctly, much of the supposed conflict with the standard cosmological model becomes less severe. The universe is not necessarily breaking its fundamental rules. Instead, astronomers may have misunderstood what was producing the light. Spectroscopy has become the key to solving the puzzle. In one major study, roughly 70% of the observed little red dot targets showed evidence of gas moving at around 1,000 kilometers per second. Such rapid motion is difficult to produce through ordinary star formation alone. It is consistent with gas moving in the extreme environment surrounding an accreting supermassive black hole. That does not mean every little red dot is identical. Some may contain dense stellar populations. Some may be dominated by black hole activity. Others may contain a combination of both. The category is based on appearance, not on a single confirmed physical explanation. Yet new evidence is making the black hole interpretation stronger. One important object is called CANUCS-LRD-Z 8.6. Webb observed it as it existed only about 570 million years after the Big Bang. NIR spec data confirmed that the compact system contained an actively growing supermassive black hole. Like QS01, it had produced relatively few heavy elements, indicating that it was still at an early stage of chemical and galactic development. The existence of another rapidly growing black hole so early in cosmic history shows that QS01 is not an isolated problem. Then, in June 2026, researchers announced the most detailed spectrum yet obtained from a little red dot. The object is called GLIMPS-17775. It existed later than QS01, around 1.8 billion years after the Big Bang, but an extraordinary combination of long Webb observations and gravitational lensing gave scientists an unusually clear view of its spectrum. Webb observed the source for approximately 30 hours. The magnifying effect of a foreground galaxy cluster increased the useful detail to a level comparable to roughly 80 hours of observation without lensing. Researchers identified more than 40 spectral lines. These included features associated with hydrogen, helium, oxygen, sulfur, and a dense collection of iron lines. Several independent clues pointed toward the same physical picture. GLIMPS-17775 appears to contain a rapidly growing supermassive black hole hidden inside an extremely dense cocoon of partially ionized gas. The gas absorbs and scatters radiation produced near the black hole, then releases that energy in a form that creates the object's unusual red spectrum. Researchers describe this model as a black hole star. The name can be misleading. A black hole star is not a normal star containing a black hole in the usual sense. It is a proposed system in which a feeding black hole is surrounded by such a thick, compact envelope of gas that the entire object produces a smooth, star-like appearance. In GLIMPS-17775, many spectral lines could not be explained by a simple rotating gas cloud. The best-fitting model included electron scattering inside a dense layered cocoon. High-energy radiation was also required to produce the observed iron and oxygen features. A rapidly accreting black hole provides a natural source for that energy. This does not mean the mystery of every little red dot has been solved. GLIMPS-17775 existed later than the earliest examples. Different objects may represent different stages or environments, but it connects several previously separate clues. It shows how a black hole hidden inside dense gas can create a compact, extremely red source. It explains how an object can appear bright without requiring an impossibly massive stellar population. And it offers a possible evolutionary path. A young black hole may begin deeply buried inside gas. As it grows, radiation and outflows gradually disrupt the cocoon. Star formation may spread outward. The surrounding galaxy may become larger and easier to see. The central object may eventually emerge as a more familiar active galactic nucleus, or quasar. This may explain why little red dots appear during a limited period of cosmic history and then become rare. They may not simply disappear, they may transform. Webb has also found evidence that early galaxies changed their surroundings more quickly than expected. During the universe's first several hundred million years, space was filled with neutral hydrogen. This period followed the release of the cosmic microwave background and is often associated with the cosmic dark ages. As the first stars, galaxies, and black holes began producing energetic radiation, They stripped electrons from neutral hydrogen atoms. This gradual transformation is known as cosmic reionization. Neutral hydrogen absorbs a particular form of ultraviolet light called Lyman alpha radiation. Astronomers therefore expected Lyman alpha light from the earliest galaxies to be heavily blocked by the neutral gas between those galaxies and Earth. Yet Webb has detected surprisingly strong Lyman alpha emission from some extremely early systems. One example, JWST-GS-Z13-1, existed around 330 million years after the Big Bang. Its light suggests that energetic activity may already have created a bubble of ionized hydrogen around the galaxy, allowing some Lyman alpha radiation to escape. The exact mechanism remains under investigation. Intense star formation could have produced enough ultraviolet energy to clear a path. Nearby galaxies may have contributed. Accreting black holes may also have played a role in some regions. These observations do not prove that the standard history of the universe is wrong. They suggest that the first luminous objects may have formed, grown, and altered their environment more efficiently than earlier models assumed. That distinction matters. The standard cosmological model describes the universe on its largest scales. It includes cosmic expansion, dark matter, dark energy, and the gradual growth of structure from early density variations. Webb has not overturned that entire framework. Many early claims of galaxies being too massive for cosmology weakened after improved distance measurements, better stellar models, and recognition that black holes could contribute a large fraction of the observed light. The remaining tension is mainly about astrophysics. How quickly did gas cool? How efficiently did the first stars form? How large were the first black hole seeds? How often could black holes grow faster than the conventional Eddington rate? How strongly did black hole radiation control star formation? And how did these processes interact during the universe's first billion years? Computer simulations include all these processes, but they cannot calculate every atom, star, explosion, magnetic field, and gas cloud directly. Researchers use simplified prescriptions based on observations and theoretical models. When Webb finds an object like QS01, scientists do not necessarily discard the entire simulation. They revise the assumptions controlling black hole seeds, gas accretion, stellar feedback, chemical enrichment, and galaxy formation. QSO1 may require models in which heavy black hole seeds are more common. Little red dots may require a prolonged phase of obscured black hole growth. Strong early Lyman alpha emission may require ionized bubbles to form sooner around some galaxies. None of these changes is small, but they are not the same as saying that all of modern cosmology has collapsed. Science advances by separating a genuine contradiction from an incomplete model. Webb is giving astronomers enough detail to make that separation. The next stage will require more than finding additional red dots. Researchers need to measure how gas moves inside them. They need to separate light produced by stars from light produced by accretion. They need to determine their chemical composition. They need to search for faint stellar structures around their bright centers. They need X-ray, radio, and longer wavelength observations from other observatories. And they need larger, carefully selected samples to discover whether QSO1 represents a common beginning for supermassive black holes or an unusual path followed by only a few systems. Gravitational lensing will continue to be essential. Massive galaxy clusters can magnify sources that would otherwise remain beyond Webb's practical reach. But lensing also introduces uncertainty. Scientists must carefully model how foreground mass bends and amplifies the background light. Dust creates another challenge. It can hide stars, alter colors, and change the apparent brightness of a source. Even spectra require cautious interpretation. Different combinations of gas density, temperature, motion, and radiation can sometimes produce similar features. That is why QSO1's direct dynamical measurement is so important. Instead of relying only on brightness or the width of one emission line, researchers trace the gravitational effect of the central mass on orbiting gas. The movement itself revealed what was hidden at the center. A 50 million solar mass black hole existed only about 700 million years after the Big Bang. It occupied a system only around 1,300 light-years across. It represented at least two-thirds of that system's mass. And it was surrounded by gas containing almost nothing beyond hydrogen and helium. The result does not tell us exactly whether QS01 began as a direct collapse black hole, a primordial black hole, or an unusually successful smaller seed. But it places strict limits on every explanation. Any successful theory must create a massive seed early enough. It must supply enough material for rapid growth. It must explain why the host galaxy remained so small and chemically primitive. And it must account for the growing population of similar compact objects appearing in Webb surveys. Before Webb, astronomers knew that enormous quasars existed less than 1 billion years after the Big Bang. The mystery was how those mature cosmic monsters had grown so quickly. Now Webb may be revealing the missing stages. CANUCS-LRD-Z 8.6 shows an actively feeding black hole only 570 million years after the Big Bang. QS01 shows a system in which the black hole dominates almost everything around it. Glimpse-17775 shows how a dense gas cocoon can hide and transform the light from a rapidly growing black hole. Together, these objects suggest that the early universe may have experienced a widespread period of concealed black hole growth. The first supermassive black holes may not have waited for large, mature galaxies to form around them. Some may have appeared early, grown inside dense clouds of nearly pristine gas, and influenced the galaxies that later developed around them. That possibility changes one of astronomy's oldest origin stories. Galaxies and black holes may not always have followed a simple parent and child relationship. In some systems, the galaxy may have created the black hole. In others, the black hole may have begun shaping the galaxy almost from the start. Webb was built to see the first stars and galaxies. Instead of providing one clean and simple timeline, it has revealed a universe filled with multiple paths. Small stellar seeds may have grown gradually. Heavy seeds may have formed through the direct collapse of gas. Some black holes may have spent millions of years hidden behind thick cocoons. Some galaxies may have converted gas into stars with unexpected efficiency. And in rare environments, black holes may have become the dominant structures before their galaxies had fully emerged. That does not make the universe impossible. It makes its history more complicated than the version scientists could see with earlier telescopes. The faint red points in Webb's images may look insignificant. Each one occupies only a handful of pixels. But inside those pixels are clues from a time when the first major structures were beginning to form. QS01 is one of the clearest clues yet. It is not literally a black hole floating alone in empty space. It contains gas and probably a small developing stellar component. But compared with the black hole at its center, the surrounding galaxy is barely established. The heart appears to have grown before most of the body. More than 13 billion years later, its ancient light reached a gold-covered mirror orbiting far beyond Earth. Webb separated that light into wavelengths, mapped the movement of hydrogen, and allowed scientists to weigh an object from one of the earliest periods in cosmic history. The answer was not the one many models expected. The black hole was already enormous. Its galaxy was not. And the question of which came first can no longer be answered in only one way. As Webb continues observing little red dots and other early systems, some of today's mysteries will become clearer. Others will probably become more complicated. That is not a failure of astronomy. It is the reason telescopes like Webb are built. A powerful observatory does not only confirm the universe we expect to find, sometimes it reveals the universe that was there all along. If you enjoyed this journey into the early universe, subscribe for more science documentaries based on real discoveries, and leave your answer in the comments. Which do you think came first in systems like QS01, the galaxy, or the black hole?